We're back. I have no idea what part we're on as far as notes are concerned. We're just going to say, let's just do this thing. Excellent. So screen full and pick up where we left off. This constant increasing thing, I really want to graph this by hand because it's good review on graphing. So the big piece, each of those, a piecewise function means you actually graph those three functions listed there, but for the prescribed domain. So it's not the whole thing. So I'm pulling up, let's see, a little grapharoo. I'm going to be as careful as I can with this. It's going to look good. Yeah. And it says I'm going to be graphing f of x equals -5 for x less than or equal to -3. So you got to -3, 1, 2, 3. And I go down to -5, 1, 2, 3, 4, 5. And I'm going to put, it says it works from there left. Okay, I'll do a highlighting action to make you see what I'm talking about. That one corresponds to this. Yeah? Okay. Then we're going to do that 2x plus 1 is for the domain -3 to 2 on the inside there. So I'm going to draw in a line with a slope of 2, and a y-intercept of 1. Can I do this? Yep. So if I go to a y-intercept of 1, and I go up 2 over 1 from there, so here's a y-intercept of 1. I'm going to zoom in on that. Up 2 over 1, up 2 over 1. It's a height of 5. And from y-intercept of 1, I go down to left 1, down to left 1, down to left 1. I land on the other point, which that's cool. Okay, so that's the internal part. It says you go until you hit x equals 2. So I stop there. And it says not equal to, right? It had a greater than or just two less than symbols. So what I should actually have there is a hole at the end of each of these little lines. This hole gets filled by the graph x equals or y equals 5. So this one's filled in by the graph that we had initially. Okay, so there's a hole that gets filled in. Okay, and up here it has a hole because of this less than 2. It doesn't actually touch 2. Then we go to the last one, f of x equals 5 for anything greater than or equal to 2. So I put in a horizontal line starting at 2 at a height 5, and that fills in that hole. So it's a nice continuous graph because where there's a hole in one graph, it fills it in with the other. So that's pretty slick looking. I got a color code uphill like that. I'm not doing it by any particular means. I'm just highlighting because it's fun. Okay, got it, and there. Good. That's the graph. Very cool from a very simple absolute value function. Just so happens you can graph. I did it on a graphing calculator when I was up at the board earlier, but trust me, that's exactly what it looks like on your calculator. I'm going to pull up ours very shortly and we'll graph some stuff. The main thing is, though, also noting interval notation. I'm going to slap that in there real quick. That less than or equal to -3. This graph is constant from -infinity to -3 inclusive, and then decreasing. That should be a different color. It's so hard to read. Red. Should be -3 to 2, but those are -3 to 2 parenthesis. Sorry, that's overlapping, but same thing as I'm seeing right here, but written in interval notation. And the last one is greater than or equal to 2, which means not a parenthesis, but a bracket at 2 on to infinity. Okay, just to reinforce, that's the domain that goes with each of those in interval notation. All right, this next piece, we got to fill in 7. There's nothing in there. I'll go ahead and jot these in there. X squared, or x plus 2 squared. This is where we're going to start graphing pretty soon. Okay, got that one. So analyze increase and decreasing behavior. Totally dirty dozen variety. You know this graph. Do you know what the parent function to this one is? What's the original? What's the dozen? What kind of pictures are you going to make? You can draw it in the air if you want. One of those? Parabola? Parabola? Takers? You're so right. But we got a little piece that says go left 2 with it. 1, 2. Parabola. Should go all the way down. Got it? And that means if we're going to do increase and decrease, I'll color code. Increase, I'll do green. Decrease, I'll do yellow, green, pink. There you go. Those are the increase and decrease. My increase, I'm going to write it in just INC is a perfectly good abbreviation. Interval of increase, negative infinity to 0, but not including 0. It's not going uphill there. It's at that flat. Remember, it's level. So that's a moment of 0 slope when you get to 0. So we don't include that in the increase. Decrease is from 0 on up to infinity. It's not decreasing at 0, so we don't want to include that in the interval. Okay, so that's a nice, real clear one. Highlighter to match, decrease, and increase. I hope it. Oh, no. Yeah. Okay, okay, I gotta switch. I don't want to mess with my highlighting because that's way too good. Dang it. You were so right. Okay, backing up. There we go. Negative infinity to 0. It is decreasing. Okay, how far back do we gotta go? Thanks for not holding your breath too long there. All right, increasing 0 to infinity. Yeah? And then decrease? Dang it. Backing up again. Yeah? Whew. All right. And all that's recorded for posterity. That's even better. Oh, that's even better. Good. Let's go with it. Negative 2. Good for you. Negative 2 to infinity and decrease negative infinity to negative 2. All I really wanted to do was use the highlighter. Gosh. Yeah. We're in. Yeah? Glad you know how to do that. Okay, next piece. Another graph. Not a whole lot of variety to this. This is actually spices it ever so slightly. So let me show you something. Let's put in a squiggly line. G of x is x squared over x squared minus 1. Like that. The increase and decrease stuff, if I were to just look at this at first, one thing that should jump to mind is that we have been dealing with domain a little bit lately. So if you look at the denominator here, we're going, ooh, it's got a denominator. Oh, if it's equal to, anywhere it's equal to 0, those are illegal values. So I might even be thinking x squared minus 1, set it equal to 0, do a little solving. That'd be a really good idea. Do x is plus or minus 1. So we know that we're dealing with some vertical asymptotes at plus or minus 1. The rest of the behavior of the graph to be determined. Perfectly good time to go grab a calculator, so we're going to do that. So grab your graphing calculator, and I'll get mine. Okay, TI Smart View. It's coming right up. Come on, Smart View. Okay, you got yours. So we're graphing the x squared over quantity x squared minus 1. What's really fun about this one, have you ever proven a book is wrong? Have you ever had the satisfaction? We get to do that today. I want to show you guys a big old error in your textbook. And it's also a big old error on my math lab because I think they asked for the same thing, but they're absolutely not correct. Yeah, you can steal that one right there. It's all yours. Clear. And you're welcome. And clear. Catching up with you guys. So that's x squared over, sorry I covered it up, but hopefully you can see it on your screen. X squared divided by quantity. Any denominator, you got to do the quantity notation. X squared minus 1. Ooh, yeah. Okay, I'm going to do zoom 6 just to get the ball rolling. Ta-da! If you have on your graph, you might see some little lines that attach like piece of these random lines that you don't see in my graph. Don't worry, that's a pixelation issue. Asymptotes, sometimes on some of those calculators, it puts a weird diagonal line through your asymptotes. It's just a calculator like pixelation issue, so don't panic. Get used to seeing it. It should not have those. If you have one of the really new TI calculators, it doesn't do it, but it's the older ones. Throw in some weird lines. So I think if you zoom in a little bit, it'll disappear. Yours doesn't look like that? Oh, want to take a peek at it? I'm attached to my earplug. Come on over. Oh, that's good. And this is just what I'm talking about. It kind of looks like a weird W, like a weird cursive W. This is right, but what happens is those asymptotes, these diagonals show up. I think if you zoom in, it'll stop. I'm going to do a zoom box here. And you have the right graph. It just, one of the limitations of these calculators, especially if they're a little bit older. I think if I zoom in, I think it goes away. Yeah, but it's easier to see anyway. That way it looks better. But it should be an asymptote. It's just by error, it does an error of drawing a line between them. Okay, so yeah, if you want to see what I just was talking to Hannah about, it's just, Savannah, it was just a connector between those asymptotes for whatever reason. That's an error. There's the graph. Increase and decrease on this thing. So if I go, bring back my screen. Let's see if I can get it back up here. Come on, buddy. Yep, I'm still hooked up. Can you see me? Oh yeah, you can see me. That particular graph, we're going to sketch over here on our page. Looks awesome. It goes kind of a -1, +1. We see our two asymptotes. Graph goes up, comes over like this, and then it comes down. And the weird connectors I'm seeing in some of your calculators is it draws this weird line that kind of connects these two right in here. But those are errors. Don't worry about those. All right. Now, increase and decrease. There. We have interval of increase. I think you guys have had the idea of definitely -infinity up to that -1. So let's do that. INC will go -infinity to -1 in terms of x. Remember, I'm sliding like an imaginary vertical line across here. From what x value to what x value is this graph going uphill? Okay, I just described that there. The next one, so we'll throw a union symbol in there since we're going to do 2 side by side. It also does it from -1 until when? When does it stop increasing? 0. Yeah. Is it increasing at 0? It's flat. So I would say parenthesis. Well, that's correct, by the way, and I have the proof of it on the back wall over there. If you look on the very, 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 very back wall, I did something we do in calculus just to prove that, and the textbook puts a bracket. So if you go looking at your book and you look at my math lab, it puts a bracket in there, and that is incorrect. Because increasing means you have a positive slope, and if you get to a peak of that little central section at 0, it's the top of a hill and the slope is 0, which means it's not going uphill. I did something on there. You don't mind all the work. That's a formula that you will know and love, those of you going to calculus. But I took a derivative, and this thing called a derivative, if you look on the very top, it says f prime on the back there. And I'll put it up here on the screen too. I wrote on the back, f prime of x is 2x over x minus x squared minus 1 quantity squared. That's the derivative of this, or I should say g of x, because this one's g. So let me go in here and write g. So the notes look right. But g prime of x, the derivative tells me the slope anywhere on my graph. So if I put 0 into that thing on the back wall, this is what I did. I put 0 in for x into the derivative. And if you put 0 in there, guess what you get out? 0. Because 2 times 0 is 0 in the numerator. And then on the bottom, you get 0 minus 1 squared, which ends up just being 1. And that makes out 0. That means our slope at 0 in that graph is 0, which tells me there's no increase. And the wild thing is, it's really fun to disprove a book once in a while. But it happens. They're doing a large published work. People who edit it are people who work. They can be teachers and professors. They just send out edit copies, and they say, look for errors in this. And sometimes you miss them. And it's easy to mix. So when you guys see that in the book, do note it should be a parenthesis, not a bracket. And then decrease, the downhill stuff. My computer's a little slow. decrease